Okay, so what I'll do today is to pick up from where I left yesterday and quickly set up the stability analysis of the Swift-Hohenberg system and classify the various kinds of patterns and using Swift-Hohenberg as an example of one type of pattern. And hopefully by the end of the first half or so, I want to start looking at Turing patterns and derive the Turing instability criteria quickly. And the hope is that by doing so, and since we developed the code for a simple diffusion problem yesterday, we can easily modify that yourself to include the reactions, and you should be able to see Turing patterns coming up there. Okay, so to continue, so remember we want to look at pattern formation in a system of coupled nonlinear PDEs. And so typically what I have is a bunch of variables, U1, U2, U3. And a set of parameters, theta1, theta2. So these are the fields that I'm interested in, and these are the control parameters for the problem that I'm interested in. And my set of equations, I can represent it very abstractly as a dtu, thank you, as a nonlinear operator, nonlinear which has both the fields as well as the parameters. So that's the abstract setup, right? Most of the time we've been looking at the case where the number of parameters is only one. But I mean, as you can expect, realistic systems will have many parameters, and so therefore bifurcations are possible in many parameter directions. The way we try to analyze this system as a dynamical system is to look for the fixed points or the stationary states. And around a fixed point, we try to do the linear stability analysis. So by definition, the fixed point is such that the nonlinear operator acting on the fixed point at the set of parameters is 0. That's the definition of the fixed point. And now what you do is to perturb the system. So the other way around. You perturb the system, u as u star plus delta u, and then do a Taylor expansion of the nonlinear operator. So therefore, the nonlinear operator at u star plus delta u at the set of parameters theta will be the nonlinear operator at u star comma theta plus some linear operator. I mean, that's basically the functional Jacobian at the parameter values theta times the perturbation delta u. Okay, so by definition, this is 0. And so therefore, what you land up with is dt of the perturbation is this linearized operator evaluated at the fixed point times delta u. So you look for separable solutions. Of the form delta u is e to the lambda t times some eigenfunctions w, which are functions of space. So delta u of r comma t of r, where the w are basically the eigenfunctions. The linearized operator. Okay, so that's the most general abstract setup. Okay, now the U star, the fixed point that you found out, could be an inhomogeneous fixed point. So that means it could be a function of space. That is possible. I mean, highly unlikely in most cases, but there are some examples where you can find that. Now, the trouble is if you want to analyze the stability of that inhomogeneous fixed point. So what you have here is a linear differential equation. Remember, L is some linearized operator. So basically some like eigenvalue problem, Schrodinger equation. But if U star depends on space, then this is a linear partial differential equation with non-constant coefficients, and those are hell. I mean, there are only very few cases where you can solve things analytically. And so most of the time, what you do is to assume a homogeneous steady state or homogeneous fixed point. That is, U star is independent of position. Right? That also says that this is a PDE system with constant coefficients. So therefore, it has space translation invariance, which means Fourier basis is a nice eigenset. And that's the method that we've been using so far. And most of the time, that is what will be used in pattern formation theory as well. So if U star were dependent on space, you've already broken translation invariance. So therefore, you cannot use Fourier functions as basis set. All right. So to put things in context, so you find out these eigenvalues, lambda, and so therefore there will be some e to the iqx in one dimension, let's say, and so the growth rates will depend on the perturbation wave number, the wave number of the perturbation, and this is what we derived yesterday. Right? So we derived this for the Ginzburg-Landau model. We'll also do it now for other models. Now remember, it's not just a function of the modes, but it's also a function of the parameter set. Okay. Now there'll be a bunch of critical parameters, some theta equal to theta critical, at which you start seeing a bifurcation. That means the homogeneous state becomes unstable. So at some critical point, theta c, homogeneous fixed point U star loses stability. So depending on how it loses stability, in particular about how the growth rate looks like at the critical point, you classify the various phases. So just bear with me for a few minutes. I'll write it a little abstractly in terms of the classification, and then we'll come back and work out the Swift-Hohenberg model in detail. Okay, so for simplicity, I'll assume there's only one control parameter. Of course, you can do it for many control parameters as well. I'll define some reduced control parameter. Epsilon as basically theta or minus theta c divided by. So therefore, epsilon equal to 0 is the bifurcation point. Okay, so the crucial function is this growth rate function, which is a function of q and epsilon now. I'll forget vectors on q, we'll do it in 1D, but the analysis goes through for higher dimensions as well. And I will write this as a gamma q comma epsilon and a I times q comma epsilon. So basically the real and imaginary parts of the growth rate. Now, depending on how these numbers look like is how you start classifying the pattern forming instabilities. So first of all, I mean, you will get a pattern only if gamma is greater than 0 for some set of modes Q, right? I mean, that's what we've been doing so far. If gamma is negative for all Q and no parameter value gives you gamma positive, well, then the homogeneous state is a stable fixed point. So there's nothing else to do. So if you want to find out where a bifurcation happens, where the homogeneous state loses its stability, you basically want to look at the curve where gamma Q epsilon equal to 0. Does that make sense?
Yes.
So in fact, this is what is called the neutral stability criteria or neutral stability curve. I mean, curve if it's Q and epsilon, if not, it's surface in higher dimensions. So we'll calculate this for the Swift-Hohenberg, but just I want to set up the abstract vector. So typically this will turn out to be something like that. So you'll be plotting the control parameter and the wave number, and it'll show some non-monotonic dependence where you'll see something like that. So if you remember, the growth curve for Landau-Ginzburg looked like something like this. So where the peak was really at 0. So in some sense, you can think of it like the inverse of that. It's just a qualitative picture. So it's basically the defining condition is really the contour where the real part of the growth rate vanishes in the wave number and control parameters.
Vijay, there is a question, why is W a function of gamma?
Why is W a function of gamma? Where is W?
I think that is omega he's trying to say.
So this is Q comma epsilon. Thank you. Okay, so that's the neutral stability curve. So this is basically saying where the real part of the growth rate is 0, and you find this is a neutral stability curve, which is basically, by the way, this should be 0. So we should just go a little bit above. So what is this saying? This is just saying the following. Hey, look at a particular mode Q. So I'm going to put a perturbation like e to the iqx. What is the control parameter value at which the system becomes unstable? So this is the parameter where this is the stable regime. And this is the unstable regime. You see this, right? This is an implicitly defined curve. This is the curve on which gamma vanishes. So which means on one side, gamma is positive, the other side, gamma is negative. And gamma positive is really what we want to define as the instability region of the homogeneous state. So the neutral stability curve is basically telling you the following. I look at a particular mode Q, e to the iqx is the perturbation. What is the parameter value at which that mode starts growing? Okay. So therefore, that parameter value will depend on the mode that you put in. So typically, the growth rate, like what we had here, there'll be a particular Q at which you will hit a value of epsilon that's the lowest. So that value of Q at which epsilon So remember, I want the transition to happen at, yeah, sorry, should I just define this properly? Okay. So remember, we've defined epsilon to be this reduced parameter, which means epsilon equal to 0 is basically the point at which the bifurcation happens. And now I've drawn the curve, and the curve, the neutral curve hits epsilon equal to 0 at a particular QC. Okay. Fine. So QC is the mode which has the highest growth rate at the onset of the instability. No. We'll see something like this coming up many times. Or you can even do a local thing. I mean, you will typically have some growth, some neutral stability curve, which will have some maxima and minima. You could have multiple maxima and minima. What do you mean at a minima? I mean, epsilon is negative is the stable point. So remember, this is not a plot of epsilon versus q. Okay, so the real function is gamma. And I'm looking at the contour value where gamma vanishes. So it's an implicitly defined. So the real point why we are trying to, so if it helps, maybe you think about it in terms of the plot of gamma itself as a function of q. So typically you would have something which is for epsilon less than 0, all modes are stable. At some particular value of epsilon, which is the critical epsilon equal to 0, this just hits 0. And then above that, of course, there will be a band of modes where there will be an instability. Okay, so there will be a particular QC, right? So that's the same QC. You can look at it in two different ways.
So why, by the way, we are assuming that the epsilon increases?
Remember, if you go back to the Landau-Ginzburg or the bifurcation that we discussed, Rx minus x cubed. So I had R less than 0, something is stable, R equal to 0 is the bifurcation point, R greater than 0 is where the homogeneous state loses stability.
But in that bifurcation, the pitchfork bifurcation that we studied, in that we had two fixed points, right?
Two new things which appear after R equal to 0.
Yeah.
At R equal to 0, the x star equal to 0 fixed point loses stability. Okay, so and we are doing the linear stability analysis about the x star equal to 0 fixed point. So I've chosen some fixed point U star, right? So bear with me for 2 more minutes and I'll show you some examples, then it might help set up things. Yeah. So I'll come to that. So depending on what happens there, you'll classify things. So remember, all I said is the eigenvalues of this linearized operator L. Well, the eigenvalues can be complex. There's nothing preventing, it's not a Hermitian operator. So therefore, and the eigenvalues can be complex, and in the Fourier basis, therefore the eigenvalues will depend on which mode you're looking at. And of course, the set of parameters. So you define there is QC, which is of course a function of the parameters. And you look at, just give me 1 minute, omega C, define it to be the function omega at QC, and of course the parameter values epsilon equal to 0. So depending on these two quantities, we will classify the different pattern forming instabilities.
In the plot of epsilon versus q.
Again, it's not epsilon versus q.
No, for gamma q positive or negative, you have this phase plot, right? This is phase diagram like that.
It's not a phase diagram, it's what's called a neutral stability curve.
Okay, neutral stability curve. Why is the upper one unstable and the lower?
So again, let me repeat. So I'm plotting, so there is this function. I've got lambda of q epsilon. I take the real part, call it gamma. I want to look at the case where gamma vanishes, because gamma negative, everything is stable. Gamma positive is where things become unstable. So the critical point is where gamma vanishes. That's a function of two parameters, Q and epsilon. So this is a plot where gamma vanishes. So which means gamma is equal to 0 on this orange curve. What does that mean? Gamma should be positive on one side and negative on the other side.
Is it because your gamma versus takes this?
You can draw it either way. I just defined epsilon positive and I defined epsilon to be the point where epsilon negative is stable, epsilon positive is unstable. You mean you can't have like this?
I think
Unstable being the one which is.
Why is it unstable above?
Yeah.
That depends on the function gamma, right?
Because that's your gamma.
No, I mean, we'll get gamma in a minute. We'll get gamma for a specific set of
Okay, so
parameters.
this is general.
This is a very general statement that if you have the function gamma, and I'm looking at the contour of gamma equal to 0, surely on one side it will be positive, on the other side.
Yeah, the question
That's
is
all
why
I'm
you
asking.
chose the upper side to be unstable. I
That-
understand there is one side.
That depends on the function gamma.
Okay.
but isn't it?
It can be, I mean, we'll get some particular gammas and then we'll watch the difference. Exactly. So we'll come to that in a minute.
But isn't it related to the same question that I asked, like why we are saying like when epsilon goes from negative to positive, like so I'm trying to relate it to that bifurcation diagram. So there was this U star was equals to 0 becomes unstable, and
By the way, that was for a ODE system, huh?
yeah.
Okay.
When we kind of increase the R.
Yeah.
Here we are also increasing this epsilon parameter.
R and epsilon are the same.
Yeah. So, I mean, if you look at the U star equals to root R, it's the other way around relation, right?
What is the other way around?
So for negative R, it doesn't even exist,
Yes.
but like it becomes stable after like R becomes positive.
Yes.
So it's like kind
So
of.
for the system that you're talking about, there's no Q at all. It's an ODE system.
What I'm trying to say is like when the epsilon actually becomes positive or like it increases, somehow this solution becomes unstable, right?
I don't understand what
The
becomes
gamma becomes positive for some reason.
Yeah, that is basically the definition of the bifurcation.
I'm trying to understand from this diagram, like the one that you just.
So I guess that diagram going up doesn't mean that it's going to be positive side. Some axis in the negative.
Which direction? This one or this one? This one is
Some axis going up. One side is yeah. So you think that going up means epsilon positive. That's not here. Zero one side is one direction, another side.
This one, I've defined epsilon to be something such that at the critical point theta c, epsilon is 0. And so my definition is such that if theta is less than theta c, the system, the homogeneous state is stable. And for theta greater than theta c, the homogeneous state is unstable to perturbations. So therefore, epsilon less than 0 is the stable value of the parameter. Okay, so depending on these two parameters, omega c and qc, you get the following kind of classification. So the point being that though it looks like you can have an arbitrary set of PDEs which can undergo an arbitrary set of bifurcations, and you can get really all kinds of patterns. Well, you can classify the patterns into 3 different types. And so therefore, there is some sort of a universality, like universality classes in equilibrium phase transition. So one type is called type 1, for no particular reason, Hohenberg chose it, and so we're all following it, is one where the growth curve, lambda q, or really gamma q, the real part, gamma q, has the following behavior, that it has some behavior at small q but there is typically a maximum at a non-zero Q, that's the QC. And at the critical point, this just touches the gamma equal to 0 point. And above that, of course, there is a band of wave vectors. So this is epsilon less than 0, epsilon equal to 0, epsilon positive. Furthermore, if omega c is not equal to 0, that means there is a non-zero imaginary part at this value of QC, omega evaluated there. You can also have an oscillatory instability. Okay, so first thing is, if omega c is equal to 0, then this is called a type 1 or 2 or 1 stationary instability. Omega c not equal to 0, type 1 oscillatory instability. Another class of systems is where typically there is some conservation law, and you have the following growth law. That the growth rate at Q equal to 0 is always strictly 0. So remember, Q equal to 0 is the homogeneous state. And so therefore, if you have some conservation law which says something cannot go up or down, it has to be strictly 0. So therefore, the Q equal to 0 growth rate must be 0. And you can have a situation where for some epsilon less than 0, the growth curve looks like this, and epsilon equal to 0. So again, you can have the two classifications where omega c equal to 0 or omega c not equal to 0. This would be type 2 stationary, type 2 oscillator. The third kind is where the growth rate has a maximum really at Q equal to 0. So this is again using omega c classification. This would be 3 stationary or 3 oscillator. So most pattern forming instabilities will form into one of these classes. So typically here you get a conservation law. You have a conservation law, and it's the conservation law that typically dictates this kind of a growth rate. This is typically instability of the homogeneous state itself. Remember, Q equal to 0. And if you remember yesterday when we did the Ginzburg-Landau, this is the kind of plot that we got. I will do the Swift-Hohenberg and Turing systems today, and we will see that they fall in this class. And if we get to that, I will discuss one example of a simple pattern forming system in active fluids, and we'll see that that falls in this class.
So in conservation, how do you define epsilon equals to 0 curve? Because it's gamma q is going to be 0.
So there's no pattern here, but I'll just think about the diffusion equation, 1b. And let's say I put in some simple linear term. So C equal to C naught is a homogeneous state. And so please do some perturbations, delta C, with delta C amplitude going like e to the iqx, and show that the growth rate will be basically something like dq square. dq square minus k. If k is not equal to 0, then you have something at q equal to 0, the growth rate will be non-zero. If k is equal to 0, the growth rate at q equal to 0 will be strictly 0. Of course, in diffusion, you don't have anything else happening. If I have some parameter, which I will try to derive when we do the pattern forming thing, there is some effective d, and the effective d can turn out to be negative, then you will have a pattern forming system. But still q equal to 0, the growth rate is 0. Okay, so it's a bit abstract, but this is a nice way to classify the various pattern forming instabilities. And a very large class of them actually fall into one of these three types. You don't need to remember the type 1, 2, 3. I always mess up that. All I remember is whether the growth rate is non-zero at some finite q, strictly 0 at q equal to 0, or can become non-zero at q equal to 0. That's all is the essential idea. Okay, so let's actually do this for the two cases that we were thinking about. So yesterday we did the Ginzburg-Landau model. So where we had, if you go back and look at your notes, we had GTU is RU minus U cubed plus dx square U. And we did the linear stability analysis about the U equal to 0 state, star equal to 0 state. And we found out that the growth rate, lambda of Q, is basically R minus Q square. Hopefully you all remember that. So therefore, gamma of Q is the same thing as gamma of Q comma R, for example, is the same thing as R minus Q square, whereas omega of Q comma R is 0. Okay, and the growth rate gamma is maximum at Q equal to 0, and whether it's positive or not depends on R. So R is basically epsilon. So with this classification scheme, this is basically a type 3 stationary. So today I want to set up the Swift-Hohenberg system and do a simple linear stability analysis for that. It's quite easy to do. And I don't know what to erase now. I want to retain these three types. Okay, I'll try to set it up there itself. The Swift-Hohenberg model is a simplified version for understanding, for example, the Rayleigh-Bénard instability in convection. And so I refer you to the original paper, PRA 77, I don't remember the exact reference, where you can take the original Rayleigh-Bénard system and rewrite and show that this is the dominant model that captures everything. So you have something very similar to the Ginzburg-Landau picture, except that you have a particular 1 plus dx squared, the whole square. So as usual, the homogeneous states are U equal to 0 is 1 and U star equal to plus minus root R. Can you please do the linear stability analysis for this? I'll leave it to you as a homework. So perturb around, say U star equal to 0 fixed point. As usual, do the linear stability analysis and figure out how the growth rate depends on the parameters and show that lambda of Q, the growth rate, is basically R minus 1 minus Q squared, the whole square. So therefore, if you look at this classification, this is the same thing as gamma, and omega is 0. All right, but now which one of these types does it fall into? Okay, look at the plot then and tell me that. I plot gamma as a function of q. So let's say for r negative, please think about the plot and see how it looks like. So r is negative, r and epsilon are the same here again. So for epsilon negative, what is the value at q equal to 0? Positive, negative, 0. Some negative value. And then does it monotonically go down? Does it go up and down? I'm asking you to just plot this function as a function of q for r equal to 0. Yeah, so it goes up and goes down. So this is for epsilon less than 0. What about epsilon or r equal to 0? Huh? It hits the 0 line. So basically you'll get the same thing, but just shifted up. But then there is a certain q at which just about hits the x-axis. And what about further? If I make r positive, okay. So what does this mean? This means that at epsilon equal to 0, the critical point, you have exactly one mode which is growing there, and it's just about hitting the instability point. Anything epsilon greater than 0, infinitesimally greater than 0, there is a band of modes, right? So you'll get some. And so therefore, all those modes start growing. Which mode has the highest growth rate? Well, QC equal to 1 here in this non-dimensionalized units. So there is a certain length scale, 1 by QC, and that's the length scale on which the pattern starts appearing. So there was a question yesterday, and how do I know what is the wavelength of the pattern? What is the length scale? So there you go. Now, close to the onset and doing some local analysis here, you can do more predictions about the amplitude equations, how pattern wavelength, how patterns get selected. I don't think I'll be able to go into that part of the story at all. So can you stare at the types and tell me what kind of instability this is? 1, 2, 3, S and O. 1 what? Okay. So 2.5 lectures later, I have enough stuff to actually go to biological patterns. So
Vijay, so in this case, I mean, once it becomes unstable, is it known exactly what the stable solution is?
in one dimension, you will get some periodic thing. I mean, you don't know the exact
There's no
analytical form now.
Is it?
It is non-linear.
Huh?
It's a non-linear PDE.
Yeah, no, but sometimes 1D at least you can get some example.
Yeah, some approximation, long wavelength, you can do some.
Okay.
In more than one dimension, you start getting all these things that you get in Delavan. You first you get stripe-like rolls, and if you go further, they'll break up into hexagons. All those things will start appearing. This is the primary bifurcation. Further on, there are more bifurcations.
But basically, you get a periodic pattern.
You get a periodic
wavelength QC.
Yes. Close to the onset of the instability.
Right. Yeah.
Far away, of course, there'll be other nonlinearities will come in, and you can't predict anything. So close to epsilon, slightly greater than 0. Yes, QC is the dominant wavelength of the pattern.
And so basically, you are just adding a del X4 extra, right?
Where is that?
Also,
Also a del
change
x square.
with a negative. Is it negative or positive? The sign
No, this is minus. So you expand it out, everything will become
minus.
minus.
So it's a sign has changed from del x square.
Yeah, but then there is a del x4 with also the same.
Right,
sign,
yeah,
so
yeah.
therefore it's stabilizing.
Okay, but I mean, so is it? Is there some? What is the physics of this?
So the physics of this is basically the Raleigh-Benard instability. So what you do is to set up the problem where you look at a system with a hot plate and a top plate like that, where you have a delta T temperature difference in some width delta, and you work out the full Navier-Stokes equation coupled to the heat conduction equation. And then you can show that if you look at the dominant mode, which will actually be a mixture of the, in the midplane, the Z component of the, okay, this is not U, the Z component of the velocity and the temperature, some linear combination of that, that will turn out to be your U. And that is the dominant. So this is actually derived in that, I'll put up the reference to that original paper, the Swift-Hohenberg. No, it oscillates.
No,
Remember,
because finally it will be in, there's another I, right? IQX, it will go to the IQX, right?
Repeat that again.
No, when you have non-zero, see, this gamma gives you the pattern in the real space, right?
No, everything is in real space.
No, I'm saying that this Q is in the Fourier space, right?
Yes.
No, right?
Yes.
So this gamma gives you the oscillation in the real space,
Yes.
right?
Yes.
But now if you have a non-zero omega, so that means that is it oscillation in time or the amplitude of the pattern will go on increasing or decreasing?
Both. Remember, it's e to the lambda t.
Okay.
So it's I omega t.
Yeah, yeah.
So that if omega is non-zero.
So then you have a pattern both in space and time, basically. Okay. Yeah.
So in fact, if you remember, we did this half bifurcation yesterday or day before yesterday, where we looked at the ODE system. And at some point of the critical parameter, the real part of the growth rate was non-zero, positive, and there was a non-zero imaginary part. So that means the homogeneous state became unstable, went into some other state, but that state had a non-zero omega, which means it went round and round. So thanks for asking that. So this typically leads to waves. There is a non-zero QC, there is a non-zero omega C. So typically leads to traveling waves. You can have scroll waves, spiral waves, very complicated set of patterns, but typically this is the condition. In these ones, if time permits, or I'll give you homework, I'll give you an example where omega is not zero. Okay. So you will, or we'll see when we do the brush later. So you can get patterns which are spatially periodic, but are also going up and down in time.
Sir, I have a question. So if when this system moves out of this homogeneous state, which heterogeneous state it will choose? Do we have a criteria for that?
That's exactly what we discussed right now. No? So at the onset of the instability, epsilon slightly greater than zero, what you will get is a system, is a state, it's a pattern state, which has a periodicity, and the wavelength will typically be 1 by QC. In one dimension. In more than one dimension, you have other patterns. I mean, if you go further in the parameter space, you can start going from one-dimensional roles, which is like varying patterns in only one dimension, to something that becomes hexagonal-like in 2 dimensions. And there's a whole plethora of patterns that can come up. One can do more advanced analysis by looking at how the amplitude, remember, I'm not worried about the amplitude, how the amplitude of the modes changes near the critical onset. And one can write down a coarse grain description, which also looks like a Ginzburg-Landau picture for a different set of parameters. And that will tell you the stability of which pattern will be stable or unstable. And so therefore, it will allow you to think about pattern selection. So you can put in a pattern, an ansatz that looks like a roll pattern, variation stripe-like pattern in higher dimensions, and ask when that is stable. Or maybe you put in an ansatz like a hexagonal pattern and ask when that is stable. So you can construct a kind of quote-unquote phase diagram where you have stripe-like patterns, hexagonal patterns, or in reaction diffusion system, spot-like patterns, labyrinthine patterns, and so on. So the mathematics gets more and more involved as you go to those analysis. But I want to go to biology, so I'll stop at the general analysis here. Any discussion? Yeah.
No, is there a reason all these curves have, I mean, this kind of second derivative? Like, I mean, you haven't had any type where I don't see why it cannot be like an up parabola or something like that.
What parabola?
Like,
Up
see the
parabola.
mirror image of the first thing.
Okay, so I would typically want the following picture to be there for my system. I would want, as Q goes to larger and larger values, I want the growth rate to be negative for sure. Otherwise, there's a serious instability with the system. You're saying large Q is small length scales, and you're saying those things have positive growth rates. So the smallest scales will really diverge very, very quickly. So if you have the system being some sort of a stability, I want large Q behavior to go negative. The only question is whether at some finite Q, gamma can actually cross zero. Exactly. I mean, so you can have a system which is, I mean, just take the diffusion equation, flip the sign of the diffusion coefficient. Rather than dq square minus dq square, you have plus dq square. Oh, you're in trouble, no? The assumption is there is a state which is stable. Maybe pattern, may not be pattern. I'm looking at the transitions from, say, the unpatterned state to the pattern. But if the state itself is not stable, I can't do anything.
Is it possible that for epsilon equals to 0, and there are two values of Q for which gamma Q is 0?
Yeah, but I mean,
So what happens then?
only, yeah, surely. I mean, those are all more complications. We'll encounter one or two of them as we go along. I am illustrating the problem where there is only one field, U. And so the growth rate is a function of Q. Just consider two fields. So there'll be two eigenvalues. Which eigenvalue should I look at? Well, the one that has the largest real part. And many a times it turns out that there are multiple modes. So there is one mode which is like that, and then there is a kink, and there is some other mode which goes like that. So this is some real part, or basically gamma, or gamma max, the max. Surely these are points where, for example, in parameter space or in Q space, the eigenvalues become complex, they might become real, they might exchange. So you'll get all kinds of patterns. So it's not that this is a one unique function, this is the largest real part. So that can have lots of discontinuities. Now,
Excuse me.
Close to the onset of the instability, the one that is having the maximal growth rate will typically dictate the pattern. There are systems where there are multiple things possible, and then it of course depends on the initial conditions, boundary conditions, and those details. Further away from the instability, you can have multiple things, but then linear stability analysis becomes less and less predictive the further you go from the onset of the instability.
Okay, cool.
Yeah.
So why are we restricting Q to only real values? So can Q take complex values as well?
Can Q take complex values? What would the Fourier transform with the complex Q look like?
We won't be able to do Fourier transforms with that. But we
So
will
then
be
why
able
am I
to
even doing all
represent
this?
Exponential functions, for example.
Exactly. So it will blow off. If the real part is positive.
So are there boundary conditions that restrict that, or so what are the boundary conditions, for example?
So like I said yesterday, I'm looking at unbounded systems in the directions that I'm, so in 1D or 2D unbounded. I'll work out bounded systems in a minute. Huh?
Does U goes to 0 at boundaries or something?
Okay, the same question as yesterday. Is that really troubles you? Think of the following. Think of periodic boundary conditions in the lateral direction.
Okay.
And think of Q as having a discrete set, but I'm looking at a function where I'm not able to resolve all these discreteness there.
Vijay, there is a question for you. Can you please repeat the last?
Excuse.
I'll answer one question from Abhishek and I'll come back. I'll repeat the question about what?
Repeat the last point of traveling waves.
Traveling waves. Yeah. So basically the idea is that if you have, so think about the following situation where you have QC not equal to 0, something like that, and omega C also not equal to 0. So therefore, the mode that has the positive growth rate will be of the form e to the QCX. Sorry, what am I saying? E to the gamma of QC plus I times omega C T and gamma, that's correct. So QCT times e to the IQX.
But in all the systems that we have yet that you have discussed up to yet, there is no oscillatory or traveling wave like solution, right?
Yeah, same question as earlier. So far I've not given you anything with omega C not equal to 0. I'll give you, maybe in the tutorial, or maybe I'll give you a homework where you can work out and show omega C is not equal to 0. So simplest example, take the system that formed the Hopf bifurcation yesterday and put in a simple diffusion there. That'll automatically give you a omega C not equal to 0.
Okay.
Yeah.
When omega C is 0, what is the time scale for going from homogeneous state to pattern state?
Okay. So I was,
how long is the pattern?
Yeah. So I didn't want to go into those details. I was thinking I'll work that out, but I'm already way beyond what I wanted to do. So it really depends on the function gamma. So like Sanjib was saying, so you have this function gamma, right? So now you look at how the function looks like around its minima. Is there a maxima? Is there a minima? Is the slope 0, non-zero? So from there, you can extract the typical plot of gamma as a function of Q. And from there, you can extract some time scales and length scales, which will depend on the derivatives of the gamma function with respect to Q, with respect to epsilon. And those will tell you the time scales on which the pattern will form and the typical coherence length scale of the pattern. This is not the same thing as QC or omega C. QC or omega C gives you the wavelength of the pattern and the frequency of the pattern. Those time scales will be the time scales on which a pattern will develop typically, and a length scale on which the pattern will be coherent. For example, you can have defects in the patterns. Let's say, I mean, if possible, we'll do that in a tutorial. It's a bit more math, and I will not be able to do Turing if you don't leave me now.
Vijay, what are the kind of conservation laws in this type 2, and like, can I see it from this gamma Q versus Q plot?
Yeah. So basically, you will have a function where gamma of Q epsilon goes to 0 as Q tends to 0.
It has to be 0 or any constant?
No, strictly 0. So any constant, this is also a constant. No? And that is also a constant. No. A conservation law.
Epsilon, say.
Just think about that. So I have some concentration field C, and I want C of xt dx integral over the whole system to be a constant. So this is basically the zero wave number Fourier transform. That cannot change. So which means the growth rate must be 0, strictly 0. Okay. All right. So my idea is the following. So this is general setup of thinking about pattern formation, and this works for biological patterns or non-biological patterns. In fact, most of the stuff we learn from fluid dynamics, which is the original hydrodynamic theory. And instabilities that were seen in fluids like Rayleigh-Bénard instabilities, where a temperature difference drives the convection state from a conduction state, or you have a higher density liquid above a low density liquid, and above a certain gravity and surface tension differences, the homogeneous state becomes unstable, or many other Rayleigh-Taylor, Taylor-Couette flows where you have two cylinders with a fluid in between, and you drive the outer cylinder and keep the inner cylinder fixed. For example, the uniformly moving flow solution becomes unstable. You start getting loads and loads of rolls, and all these things we learn from fluids. And so the standard way of thinking about linear stability answer really comes from fluid instabilities. So fluid mechanics in the bath. we also learned about these things from looking at chemical reactions. So this is the contribution from Turing, and I want to set up the Turing instability now. So the idea being that if you had a system of chemicals which are interacting with each other, think, for example, the kinds that you're looking in Supriya's lectures, is it possible that a system without spatial degrees of freedom, a well-mixed system, has a uniform state which is stable, and now I put in diffusion degrees of freedom, I give it some spatial degrees of freedom. Can diffusion destabilize the homogeneous state? It seems weird. Diffusion is always stabilizing. What's the job of diffusion? Make things uniform. So Turing discovered that yes, this is possible if the reactions satisfy certain conditions along with the diffusion coefficients. So it seems weird that a phenomena like diffusion, which is always homogenizing, if you satisfy certain conditions, can actually lead to non-trivial spatial patterns. So this is 1952 Turing's paper. So I won't work out that paper. I'll work out some modern version of that. So I'll keep the 3 types. I'll erase the others. So our picture will still be the same, that we'll look at a reaction diffusion system or any set of PDEs. We'll look at a fixed point, and as usual, unless it's a homogeneous fixed point, it's very little that we can do. So we'll assume a homogeneous fixed point. So therefore, Fourier modes will be nice eigenfunctions. So we'll be able to expand things there. And then see that if there is diffusion, is it possible that the homogeneous state becomes unstable? And what is the criteria for that to happen? So Turing's original idea, if you read that paper, you must read that paper, was really to understand if such patterns can explain many classes of biological phenomena, particularly embryogenesis and so on. I mean, he goes on to speculate a lot by saying, oh, surely mechanics is important. I'm completely forgetting that, but let me just look at chemistry alone, chemistry plus diffusion, and see if that itself is sufficient to give rise to patterns. And he speculates a lot about, of course, future people will look at mechanics. Mechanics must be important. How does, and so the modern story is really rethinking Turing's ideas in the context of mechanics, active mechanics. Okay, so look at a class of pattern forming systems now, which are called the reaction diffusion systems. So one of the references that I gave as a nice review paper by Kondo, which really discusses reaction diffusion systems as a very nice framework for understanding biological problems. There's a huge range of systems, biological systems within which you can understand. So the idea is still something very similar. So let's say I have 2 chemicals whose concentrations I denote by U1 and U2. So I'm doing deterministic modeling, no stochasticity. I'm assuming there are a large number of molecules of these things, so I can represent them by concentration fields. No stochasticity in number fluctuations. I'm also going to neglect noise in the equations of motion. Same things that we've been pursuing so far. So these are the concentration fields of the chemicals. If you have a well-mixed system, that means there's no spatial degrees of freedom, or diffusion is so high that things well-mixed system, not points. Let's say the 2 equations satisfy these. So F1 of U1 comma U2 and dt U2 is F2 of U1 comma U2. F1 and F2 represent the chemical reactions. So they could be simple polynomials, they could be something that gives you saturation like Hale coefficients and so on and so forth. But basically something that will change U1 and U2. Now, this is a system of 2 coupled ODEs. And after yesterday's tutorials, you are all masters at solving that. So you should be able to solve that, get the fixed points, analyze the stability of the fixed points, and even far beyond the stability, you can do numerical simulation, look at the solutions, and find out all the fixed points there. Okay, so let's say we found a fixed point. There could be many fixed points, but let's say we found one of them. So found a fixed point, U star, which is basically some U1 star, U2 star. And you did some linear stability analysis, and it showed that this system, this fixed point, is stable. Okay, so the ODE system, the non-spatial version, the fixed point U star, U1 star, U2 star, linear stability analysis tells you that the growth rates are negative. So that means that if you take the system, do some small perturbations in U1, U2 directions, the system comes back to this fixed point. Everything is nice, cool, and stable. So can you please set up the linear stability for this and tell me what does that mean in terms of these functions? That will be useful later on. So I will do the following, that I will do perturbation as usual. And then I will get the Jacobian matrix, which if you just stare at the ODE system is basically the derivative of F1 with respect to U1, F1 with respect to U2, F2 with respect to U1, F2 with respect to U2, whole thing evaluated at U1 star. So this is a 2x2 system. And so I'll just rewrite this using a bunch of numbers. So call this A11, 12, 21, 22. Remember, these are derivatives evaluated, so they're basically numbers. So that's my Jacobian matrix. All should know this. The two eigenvalues of this matrix can be written in terms of the trace and the determinant. So there'll be the trace of J plus or minus square root of trace square minus 4 times determinant divided by . So if the homogeneous state, if this state, I mean, there's no homogeneous, it's an ODE system. If the fixed point U star stable implies the real part of the eigenvalues or the real part of the eigenvalue with the largest real part, it's always difficult to say this, is negative. And so I leave it to you to convince that this is possible only when the trace of J is negative and the determinant of J is positive. Can you check that, please? There are two eigenvalues, and I want them to be such that I can have complex eigenvalues, that's fine. But I want the real part, both the eigenvalues, to be less than 0. And just check if this is true. Make sense? Agree? Okay. So if that is true, what does that say in terms of the A11, A12, A22, A22, blah, 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 blah. So this basically says that A11 plus A22, which is the trace, must be less than 0. And A11 into A22 minus A12 into A21 should be greater than 0. So far, so good? So now I say, I take the system and all I do is add diffusion. So that means my equations will become so the F11, F1, F2 still satisfy this criteria. So that means if I did not have diffusion, this state is a stable state. Question, by adding diffusion, can I actually say something about the coefficients such that this state becomes unstable to inhomogeneous perturbations, perturbations with a non-zero Q. And so therefore, you can start developing a pattern with a non-zero Q. So remember, the sign of A11, A22 is not fixed. What is fixed is this relationship between these numbers. Agree? Now, I won't go through the details. Again, you should be able to do this. So you take the same homogeneous steady state, homogeneous fixed point. As usual, you run through the machinery of linear stability analysis. U1 star, U2 star. So you perturb it, you look at the linearized equation, find out the eigenvalues, since it's a homogeneous steady state, space translation invariance, Fourier basis, do the eigenvalue calculation. Again, you'll land up with a Jacobian matrix, but this time, the Jacobian matrix will be a function of Q. And can you stare at this and the diffusion equation and tell me what should the matrix look like? The only change will be agree? Okay. So remember, this is now a function of Q. So can you get an instability at Q not equal to 0? In other words, I'll look at this Jacobian matrix. I'll have its eigenvalues, which will be a function of Q and all the set of A11, A22, da, 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 and also the D1, D2. So maybe I'll call that as usual theta, the set of parameters. Which you can write in again in terms of the real and imaginary parts. And so if you want an instability, that means that is there a set of parameter values such that gamma at some set of critical parameter values can actually become positive. Agree? That's the definition of the instability. And so now our job is to just do the following. Analyze the eigenvalues of this matrix as a function of Q. Use the fact that the A11, A21, blah, blah, blah are constrained by these relations in the box. Why did we get them? Because we said that in the absence of diffusion, I want this fixed point to be a stable fixed point. So therefore, even in the presence of diffusion, the Q equal to 0 state, which is basically the homogeneous state, without diffusion is stable. And so now if I just add diffusion, can that destabilize the homogeneous state? I hope you remember this. I'm going to erase that. So now for the Jacobian matrix JQ, I have now the trace, we'll just call it by T, that's a function of Q. Right? So that is basically A11 plus A22 minus D1 plus D2 into Q square. There's also the determinant delta. A11 minus D1 Q square into A22 minus D2 Q square minus A, the cross terms, the A12 into A21. So all that is required now is for you to think about the eigenvalues of a 2x2 system and just ask the following question. We said that if I have a 2x2 system, eigenvalues are related to the trace and the determinant. If I want both the eigenvalues to have negative real parts, this is the condition to be satisfied. So therefore, if this is not satisfied, then you have at least one eigenvalue with a positive real part. Or in other words, if I set this equal to 0, that's the bifurcation criteria. That's the critical point at which you will start getting a positive eigenvalue. Agree with that? So now you have something which is a function of Q. And so now our job is to just ask the following. There are these constraints on A11, A22, and I don't want to satisfy the stability constraint for a 2x2 system. Is there a value of Q? And are there some constraints on the parameters 11, A11, A22, D1, D2, such that this is possible? So if I want an instability, a finite non-zero wave number instability will happen when the trace TQ is less than 0 in fact, you also have the trace. Where are the dusters? Why do I keep on? In fact, you can also look at T0, which is just the wave number at the trace at Q equals 0, which is basically the same thing as the ODE system. But surely this is going to be less than that, and that is going to be less than that. So I want the instability when this is satisfied and when the discriminant well, stare at the discriminant. I mean, it's some function of Q, and it's an even function of Q, so it's basically Q square. So the critical, the criteria, the instability criteria will be satisfied when delta Q is 0. So as you can see, it's something which has a Q square and a Q4. Reminds you of one plot that we did earlier. And so what we would like to find out is when does this happen? And so I'll just take the Q square derivative of the discriminant. And I'm going to set that equal to 0. Why? I just want to find the maximum of this. And when is that maximum, positive or negative? That's all that matters. Agree? Yeah.
For instability, TQ should be greater than 0.
TQ should be, did I screw up the thing? Yeah. No, true. So this I was just saying for a general Q. So I want the instability when TQ is greater than 0. So this is just a statement about the criteria. It's not necessary. Yeah. No, I also want this to be negative. No? No, TQ can be, I mean, TQ will have to be positive for an instability. Just think about it. If TQ is negative, then both eigenvalues will be negative.
See, even if this trace is negative, see inside the square root, you have a trace square. And if the determinant is negative, then you have a plus sign. So then there'll be one root which will be positive.
But that still depends on the relationship, no? There's no.
Yeah, I'm saying that one root will be negative, one root will be positive, and that will set up the instability.
From definition of TQ also, I think it always has to be negative.
No, TQ always has to be negative, right? Because TQ is T0 minus D1 plus D2 Q square.
It will be negative.
Just hold on. So we found out T0 is less than 0.
Yeah.
Okay. And now to T0, I've added something which is definitely going to be negative.
Yeah.
So therefore, this is always satisfied.
Yeah.
This is always true.
Yeah.
Okay. So therefore, the only way I can satisfy this condition is
exactly. Yeah. And that's enough because one root will be positive.
This is just an observation. Maybe I shouldn't put it. This is confusing. I wish there was a control cut paste thing. Never a cut paste on the board. So you can just observe this from here. That TQ is less than T0 is already less than 0. Okay. And I'll get an instability only when I can satisfy delta Q less than or equal to 0. And so the critical point is when delta Q is equal to 0. So I want to find out where delta Q has a maximum. So I'll do the derivative of delta Q with respect to Q square, set it equal to 0. And so this is basically, if you stare at this for a few seconds, D1, D2, Q square, D1A22 minus D2A11. So the Q that satisfies this is basically half A11 by D1 plus A22 by D2. Call that some Q. Okay. Remember, we already have some statements about A11 and A22. So the sum of them must be positive. Okay. I don't know anything else, but the sum of A11 and A22 should be positive. And I also want the following, that I want my Q0 square to be, this is square. I want my Q0 square to be a positive number. I screwed up the algebra? No, I have not. No, I'm fine.
I think there should be like A11 upon D2, isn't it?
Repeat that.
A11 upon D2.
A11 upon D2. D1, D2, D1, A22. No, it looks fine to me. Just take the derivative of this and see. There will be the cross terms, right? So D1 will go with A22 and D2 will go with A11. There will be a D1, D2, Q4.
Okay.
That's fine, no? And then just solve for Q from here.
Shouldn't it be 2 D1 D2 Q squared?
There should be 2 where?
2 D1 D2 Q squared. Since you're
2
taking
D1
derivative of Q4.
Yeah. And that's the half. Yeah, you're right.
Sir, are you finding the extrema of delta Q?
Yeah. Because I want it to be positive. I've shown you that Q equal to 0, this thing is positive. And so I'll want to satisfy the criteria that's negative. So I just want to find out what is its maximum value, maximum or minimum value, extrema. And I'll set that equal to some 0. So surely that's the point when it changes sign. Make sense? Okay, so that's the most general thing that you can get. So now, like what?
6 over.
And it's some even function of Q, so you take it with respect to Q squared. So you always have a Q to minus Q. Okay, so that's the general guide. So this is the Q naught at which delta Q vanishes. And so therefore, if I go beyond that point, delta Q will actually change sign. And so therefore, that signals that one of the wave number, the eigenvalues can become positive, the real part. And so therefore, there's an instability. Now, that's all I can do in general. But you see that I can't satisfy this unless I have some statement about A11, A22, and so on. Remember, D1, D2 are positive. So if I choose A11 to be positive and A22 to be negative, but still satisfy A11 plus A22 less than 0. I can define 2 length scales in the problem, which is basically L1 square as D1 by A11 and L2 square as D2 by A22. And so my Q naught square is basically half of modulus of A22. Basically 1 by L1 square minus 1 by A2 square. So the criteria for the instability at a non-zero Q naught is basically that A11 by B1 or in terms of the rates, A22 modulus by A11 okay. So that's the Turing criteria. So that's the math. I'll interpret what it means in a minute. So see if you agree with this so far. Repeat that. Why do I need that? Remember, D1, D2 are positive. If both A11 and A22 are also positive, of course you can trivially satisfy that. But then I can't satisfy the condition that the non-spatial state is stable. So I want one of them to be negative. Both negative is fine, but both positive is not allowed. So I want at least one of them to be negative. I just made a choice. I'll choose A11 to be positive and A2 to be negative. You can do also the other way around. Is that fine? Correct.
Then the derivative has to be 0, saying that lambda q at some q is
Yes. Maximum, yeah, it's basically extrema. Extrema, yeah.
Yeah. So why is that criteria?
Which criteria?
Even if I mean this minimum criteria, extrema criteria.
So just think about the analysis. Again, go back here. So this makes sure that both eigenvalues are negative, real parts are negative. So if I want an instability, then I want one of the eigenvalues to have a positive real part. And we just boil down that to the criteria that it's really the determinant that controls the game. And now the determinant which I worked out here, it's obvious that it has some extrema somewhere. And so therefore the determinant will maybe look something like that. And I'm trying to find out what is the Q at which it has a minima. And at that Q, put that value into the delta Q and ask delta Q to be equal to 0. So below that, this will cross the 0 axis, right? Where is lambda Q? Yeah. Yeah.
That is the criteria.
Yeah.
And you're saying it will not cross.
It has to cross, and so I want it to be, I mean, so from here it's clear that it has some, this is the maximum value, but I want the number, the actual value to be negative. So I'm going to put that in here. So this is the Q that's satisfied. And you stare at the delta Q definition from here. And also the fact that Q naught square should be positive, but satisfying A11, A22, sum should be negative. So at least one of them should be negative. And this is possible only when D2 by D1 is greater than mod A22 by A11. Is the math fine? I'll make the interpretation now in a minute.
So what is the parameter that we are changing, we might change here?
Yeah, so there are multiple parameters now, that's the trouble. So you learn the basics by using one parameter, but a realistic system will have multiple parameters. So far, so good. Go back to the differential equations. So I had U1 dot as F1 of U1, U2, and U2 dot as F2, U2, U1, U2. And I said we are going to look at some fixed point. And we evaluated the Aij as basically the derivative of Fi with respect to Uj, but at the fixed point, U star. So if something like A11 is positive, what does that mean? That means U activates itself. U makes more of itself. There's a positive feedback. Yeah.
Why do we get not from
I also, so this is the Q naught at which this becomes minima.
But that's exactly the point, because it's a quadratic equation in Q square.
Which one is a quadratic equation in Q
Capital
square?
delta Q.
No, it's not.
It's a quadratic equation in Q square.
In Q square it is, yes, yes, yes.
Since then it will have a this, and when the roots are equal, that's when capital delta Q is 0. That means capital delta Q is 0 is the point where it's minima also.
Yeah, I mean, work out whichever way you want. I mean, so you basically want to find out the point where this curve touches 0.
We need to put an extra condition on that. It should be 0. There could be a curve that it do not cross the 0 point.
So I only want this condition. So it's just simple 2 by 2 system, work out whatever you want to, and the end result will be that. Since I'm running out of time, I'll just interpret this and I'll stop. If you want, we can discuss later in the tutorial the more algebra. So the statement here is therefore that if A11 is positive, what does that mean? That really means as a chemical concentration, U makes more of itself. If A22 is negative, it means U2 inhibits itself. So this criteria is saying that if in addition D1 is less than, I always screw up this. Yeah, D1 is less than D2, then you have a pattern forming instability. So slowly diffusing activator and fast diffusing inhibitor gives rise to spatial pattern. That is the Turing criteria. Chemically, it's represented by saying, let's say you have the U1, U2 fields. U1 makes more of itself, A11 is positive. U2 reduces its own production, that's like an inhibition term. And the other two things, there is a choice. I mean, you can either choose U1 activating U2 and U2 inhibiting U1, or you could have a choice where U1 activates itself as usual, U2 inhibits itself, but U1 inhibits U2 and U2 activates. Both these topologies of the networks will give rise to Turing patterns. So if the math was a bit confusing, I'm rushing through because of a bit of time, but we can work out that in more detail about whether when this criteria. So I just encourage you, just spend some time, look at delta Q, which I've already plotted here. And I want the situation where the delta Q should cross 0. I mean, that's when one of the eigenvalues will turn out to be positive. And it should cross 0 at a positive Q naught square. And so therefore, I'll be able to show that this is possible only when this happens.
Vijay,
yeah.
What did you say about this activates and this thing could be?
Yeah. So when I say something activates itself, so basically remember, these are the slopes of the F1, F2 curves at the fixed point. Yeah. These are the derivatives of F1, F2. So therefore, if this slope is positive, to linear order, how do the equations look like? So U1 dot is A11 times U1 plus A2, I forgot, is it A12, A21? Stare at that and let me know. It's A12. A12 times U2 and U2 dot is A21 times U1 plus A22 times U2. If A11 is positive, this gives you an exponential growth for U1. If A22 is negative, this gives you exponential damping for U2. So U2 reduces U2, U1 activates U1. So if you choose that, then I want the diffusion coefficient of 1 to be less than the diffusion coefficient of 2. And this is automatically saying this is enough to destabilize the homogeneous. So also sometimes written as short range activation and long range inhibition. So the range is basically because of the diffusion coefficient. So if the diffusion coefficient is very large, then of course it will spread out that effect very, very fast. If the diffusion coefficient is small, then the effect will be very localized. So the activation should be localized, short range. The inhibitory effect should be long range, higher diffusion coefficient.
So where does the parameter lie here? I mean, like diffusion constant, we can't change it in the experiment, right? I mean, like
so
the A1, A2, do they contain like some kind of parameter?
So how is it that one can actually control this in an experimental thing is quite hard. It was only in the mid-90s that people were able to actually construct experimental systems where they could control the parameters. You can control diffusion, for example, by putting in some gel and control the properties of the gel that will change the diffusion coefficient. You could put in other chemicals which will effectively change the rate parameters of the U1, U2 chemicals. And so you can get these kinds of patterns.
My question was basically,
what is the control parameter?
Yeah, so my question is basically, I'm trying to understand this this diagram of like, so when you change the parameter, this parabola will kind of
move up and down.
Yeah. So and we want a situation where this
crosses the zero axis,
touches this x-axis, right? So
yeah.
In that sense, I was asking, what parameter is that?
So it's a mixture. I mean, so it's not a single number, right? So I can control A11, A22, D1, D2, and also a Q.
So it's probably these like coefficients of this Jacobian probably is what we will.
Yeah, I mean, so for fixed diffusion constants, it's really A11, A22 that you can control. No, by definition, I mean, if it has the same diffusion coefficient, there's no way you'll get an instability. The homogeneous state is the fixed. So, I mean, getting diffusion constants to be different and getting things to activate themselves or inhibit is quite an experimental challenge. Though this has been predicted a lot to occur in biological systems, not until 97 were people able to actually identify a biological system experimentally to show that this is possibly the mechanism at work. That system was really about the fish scales. This is work by Kondo. Fantastic paper. You should read that. You can't control the parameters and all. So what you can do there is to look at the patterns, perturb the patterns in some experimental fashion, and see how the patterns respond. So it's an indirect statement about whether the Turing system is the one that it's at work. 2014 is probably the first experimental demonstration that this mechanism is really at work in how the limb of mammals forms digitation patterns. This is work by James Sharp. I can point you to the reference paper. It's a much more complicated system, but he identifies a subclass of chemicals where this criteria is satisfied. As indirect control by using some genes, which you can show will play around with these parameters. And so effectively, he can show that, for instance, remember these length scales that I drew, L11, L1 square. So these are basically the length scales of the pattern. So you could actually control the length scales of the pattern. And so think of what that means in terms of digits. So if I have a given size of my hand and I vary the wavelength of the digits, I get more digits or less digits. So he has controlled experiments in mice where he can get a mice with 20 fingers or something like that. And so, I mean, there's a nice evolutionary angle to that. I won't go into, so going from fingers to webbing, for instance. No, but you also want them to react like this. Huh. Yes. Yes. Yeah. No, okay. I don't know all the details of the experiment. It's been quite difficult. I mean, so typically the systems where you see these diffusion coefficients being different, they actually differ by a factor of 10. Until then, you really can't see. So otherwise, because that also sets the Q naught. So you want something to happen in a finite size system. Yeah, so it's a non-trivial task to actually find out. Yeah. I'll point you to some reference papers where the experiments were done.
And this gives like which like you said this.
So good. So if you actually plot the spectrum for this, you'll find that this is something where gamma Q will really have this kind of thing. This is what type? I always forget this. 1? 1S, yeah. I mean, it could be 1S or 1O as well. But for the Turing thing, where you assume the homogeneous state is stable at 0 wave number, then it turns out to be 1s, because you assume the homogeneous state doesn't even have any oscillatory instability. So Turing in his paper actually works out all these cases and shows that you can get wave-like things and so many things. So the most surprising thing is that diffusion can destabilize a homogeneous state and can lead to non-trivial patterns. Which one? So an activator is something which makes more of itself. Look at it again in the linear approximation. U1 increases U1, U2 decreases U2. Remember, A22 is negative, A11 is positive. So U1 is something which activates itself. So this is shown in chemistry by showing an arrow. U2 inhibits itself. This is like an inhibitory signal. And so if these two conditions, bit diffusion is satisfied, well and good.
We need this condition, even when you greater than A2 by A11.
Yeah, but I assume that A1 is positive, A2 is negative. Take one, A11 to be positive. Choose which one you want. Yeah.
That just means that that ratio has to be greater than the other, the right hand side. But this even greater than less than D2, where did this criteria?
So I chose A11 to be positive. Huh? So this is the full criteria. So now I can choose such that you're asking what is the relationship between A1. So choose something. So let's say A1, help me. I'm going to screw up this.
A11 is mod A2.
Greater than mod A22? Or is it less than?
D2 by D2 is greater than, so less than.
Less than, yeah. First thing is I want A22 to be negative. Otherwise, there's no way this will work out. All right. Are you not hungry? I'm hungry. Okay.
Hello.
Just one question going on. Yeah, gamma, what?
Yeah.
This diagram. So what we analyzed was just this middle graph, maybe not even that, like, because it's a matrix, right? So what are you plotting here?
Yeah. I mean, once you get delta Q, where is that? TQ on delta Q, figure out the eigenvalues, and then figure out the real part of the eigenvalues and plot the real part of the eigenvalues.
So there will be two such.
There'll be two of them. I'm just looking at one of them.
And that will only give us probably just this middle graph, because
you know the exact thing, plot it out for some parameter values. You know the full functional form of the curve. Okay, there was some question online.
Yeah, yes, sir. Like, is there any other, just a peripheral question, like, is there any other system where we can study these models for pattern formation and all that? Like maybe planetary systems, I don't know.
Planetary system. Yeah. Well, I mean, okay. A galaxy is a pattern of stars. So fine, so we can study that. So if you're asking something like, is Turing at work there? Probably not. I don't know. Doesn't seem to be, because the physics of those systems is quite different. There's lots of other things that you have to worry about. But if you're thinking, is that a pattern? Yeah. What is not a pattern?
Sense, any other studies have happened already, or?
Yeah, plenty, right? Convection spots in the sun. That's a nice example of a Rayleigh-Bénard pattern. The Jupiter's, what is that spot? Red spot. That's a weather pattern.
Yes.
So my idea was to restrict the things to in biology. This is very broad.
Thank you.
Sir, in the first lecture, you told about an experiment in which the granular particles are being oscillated on a plate. So,
what particles are oscillated?
It's a granular particles.
Granular particles, yeah.
Yes, so if I want to dig up the references for that, what should I look for?
Anything on granular physics. There's a book by.
Is it there in the ICTS?
Is there what?
So this experiment is done there in the ICTS?
Yeah, I mean, you're not the first. Of course, there are lots of other people who have done. So there's a nice book by Anita Mehta on granular physics. So that has lots of references to pattern formation there.
Thank you, sir.
Okay.
Okay, so I think we should stop break. Stop now. So we meet again at 2 p.m.